All right, now we're going to look at using related rates to solve problems involving volume. So the last four examples we looked at were area. Now we're jumping into volume. So the volume of a sphere is increasing at a rate of 550 cubic millimeters per hour. What is the rate of change in millimeters per hour of the radius when the radius is 5 millimeters? All right, so I'm going to do my best to draw a sphere here. Not a bad sphere, but not an awful sphere. It looks more like a giant eyeball. But again, the sphere is going to have a radius. And we know that the volume of the sphere is increasing. So we can draw those arrows to represent increasing. And if the area's volume is increasing, we then know that the radius is increasing. And we know that the volume is increasing at a positive 555 cubic millimeters per hour. And then we know that the radius, or we want to find the change in the radius when the radius is 5 millimeters. All right, so let's take a look at the volume of a sphere. So the volume of a sphere is 4/3 pi r cubed. All right, so now we need to identify which variables are changing. So the volume here is changing with respect to time, so it's going to be v of t equals 4/3 pi times r of t cubed. So now that we've identified which variables change with respect to time, we can take the derivative of both sides. So this is going to be dv over dt is equal to, and then we have to do the power rule and then a chain rule. So power rule says we're going to take the 3 times the coefficient and subtract 1. So 4/3 pi times 3 is just going to be 4 pi r of t squared, and then times dr over dt. All right, so then we can identify what we know. Let's see. dv over dt we know is changing at a positive 555 cubic millimeters per hour. We know that r of t is going to be 5. And then we are trying to find dr dt. So then we can substitute in these values. So we're going to have 555 is equal to 4 pi times 5 squared, and then times dr over dt. Now we just need to simplify and solve for dr dt. So let's see, we're going to have 555 is equal to 100 pi times dr over dt. And then that is going to be 500. Gosh, I don't know why I have such trouble saying that number. It is going to be dr over dt is going to be 555 all over 100 pi. And then we just need to simplify that down. So 555 divided by 100 is going to be 111 all over 20 pi. And this is going to change at a radius is a single length. So that's going to be dimension of 1, so millimeters per hour. All right, next up, a box has a width of 12 centimeters and a length of 9 centimeters. The volume of the box is decreasing at a rate of 541 cubic centimeters per second, and the width and the length are held constant. What is the rate of change of the height of water in centimeters per second when the height is 6 centimeters? All right, so a box is essentially like a rectangular prism. So we can come in here, and let's see how good my drawing skills Alright, it's been a while since I've drawn a rectangular prism. So boom, 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 and boom. Alright, not the worst, but obviously not the best. Alright, so then with a box, we are going to have a length, we are going to have a width, and we're going to have a height. So, to find the volume of a box or rectangular prism, volume is equal to length times width times height. So now I just need to figure out which variables are changing and which aren't. So we are told that the volume of the box is decreasing, so therefore volume is with respect to time. We are told the length and the width are constant, so they do not change, so we're just going to have length times width. And then we want to find the rate of change of the height, so height is going to be with respect to t. Alright, so since the length and the width are not changing, we can substitute in those values right now, 12 and 9. So v of t is going to be equal to 9 times 12 times h of t, which we can simplify that down to be v of t equals 108 h of t. So now that we have our formula, then we can just take the derivative of both sides and solve for the remaining variable. So we're going to get dv over dt, the change in volume with respect to time, is going to equal, remember that coefficient stays the same, and we multiply it by the derivative, so dh over dt. So now we only have two variables here, dv over dt and dh over dt. So the change in volume we know is decreasing at a rate of 451 cubic centimeters per second, and we're trying to find the change in height. So we can substitute this value in. Negative 541 is equal to 108 dh over dt. So now we're just going to divide both sides by 108, and we're going to get dh over dt is equal to negative 541 over 108, which that can simplify down possibly, so negative 541 divided by 108 cannot simplify down, so that is as simplified as possible. And let's see, this is going to be a one dimension, so it's going to be centimeters per second. Alright, an inverted cone has a height of 15 millimeters and an initial radius of 16 millimeters. The volume of the inverted cone is decreasing at a rate of 534 cubic millimeters per second, with the height being held constant. What is the rate of change of the radius in millimeters per second when the radius is 6 millimeters? Alright, so let's come on here. Let's draw a picture of our inverted cone. And we are told that the inverted cone has a height of 15 millimeters and an initial radius of 16 millimeters. Alright, so that means we have a height and then we have an initial radius. And now the volume of the height is going to be decreasing, so if this is our height, we're going to be decreasing, so we're going to get lower and lower and lower, which means as we get lower and lower and lower, our radius is going to get smaller and smaller and smaller. Alright, so then let's first, the volume of a cone is going to be 1/3 pi r squared h. So now we have to figure out which variables are changing. Well, we are told that the volume is decreasing, so that means it's going to be v of t equals 1/3 times pi. We know that the radius is shrinking, so it's going to be r of t, and that'll be squared. However, we are told that the height is being held constant, so therefore h is not changing. Alright, so we can substitute the value in for h. We know that the height is 15 millimeters. So this will be v of t is equal to 1/3 pi r of t squared times 15. And I can simplify that down to be 15 times 1/3 is going to be 5 pi r of t squared. Alright, so I just have to take the derivative of both sides. So we're going to have dv over dt is equal to, remember power rule and chain rule here. Power rule says we're going to take the 2 times the 5 pi, which is going to give us 10 pi. We're going to subtract 1 from the exponent, so we're going to have just 1 r of t. And then we have to multiply by the derivative, dr dt. Alright, so then we have 3 variables, dv over dt. We have r of t, and I've run out of room, so I'm going to have to write it over here, dr over dt. Alright, so we're told that the volume of the inverted cone is decreasing at a rate of 534 cubic millimeters per second. So dv dt is going to be negative 534. We are told that the radius is 6, and we want to find the change in radius. So let's substitute these values in. So we're going to get negative 534 is equal to 10 pi times 6, and then times dr dt. Alright, so then we're going to get, sorry, I need to continue my work up here. Negative 534 is equal to 60 pi dr over dt, which means dr over dt is going to be negative 534 all over 60 pi, which can be simplified down into, let's see, negative 534 divided by 60. That can be simplified down into negative 89 over 10 pi. And let's see, this is going to be in millimeters per second. Alright, and our last example for volume is a cylindrical can is partially filled with water. The radius of the cylinder, the radius of the cylindrical can, is 8 inches and its height is 9 inches. If the volume of the water is decreasing at a rate of 527 cubic inches per minute, what is the rate in inches per minute at which the height of the water is changing when the height of the water is 5 inches? So now this just sounds a little bit more confusing than it is. So let's first draw our cylindrical can here. And the thing with cylinders is that the radius is always constant. So the radius at the top of the can is the same as the radius at the bottom of the can. So what is changing here? Well, the height is changing, so dh over dt, and then the volume of the can is going to be changing. Alright, so we do have a cylindrical can, and the volume of a cylinder is basically the area of a circle times height. And now we know the volume is changing, but we did just say the radius is constant. So therefore the radius will not be with respect to time, but the height is, because the height is changing. And we are told that the radius is 8 inches, so we can substitute that in. So we're going to get v of t equals, well, 8 squared is going to be 64 pi times h of t. And now we'll take the derivative of both sides, so dv over dt is equal to, and we said when we take the derivative of something with a coefficient, we leave the coefficient alone, and this is going to be dh over dt. So our two variables are the change in volume and then the change in the height. And we're told that the volume is decreasing at a rate of 527, so negative 527. And then we want to find the change in height, which we don't know. So we can substitute in negative 527 is equal to 64 pi times dH over dt. And then we can just solve for dH over dt. So let's see, dH over dt is going to be negative 527 all over, 64 pi. And let's see if we can simplify that. 527 divided by 64 does not simplify. So our change in height is going to be negative 527 over 64 pi, and this is going to be inches per minute. And one thing to point out, you'll notice that the height of the water is 5 inches. We never needed to use that. So in this case, depending on how you solve this particular problem, you might have used that information, but in this case, it's not necessary.